Well, assalamu alaikum students and welcome to another lecture of Slate. This is me, Khawaja Yasin. Let's study chemistry. In the previous lecture, we talked about the importance of the chapter of transition metals in the P4 exam of A-level. Now, as I said, in this lecture, we will be talking about the most important topic of transition metals, which is the property of them forming complexes. Transition elements can form complexes. Now, what are complexes? As the name says, they're complex. They can make it difficult for you, but not much difficult because there are a few complexes that you need to go through and you're good to go. So, when we talk about complexes, there are various concepts that we need to revisit. This lecture would be divided into two different parts. So, in the first part, we will just introduce the terms and important concepts of complexes. And in the next one, we'll talk about the shapes and chelate effect. That's a different story. But for now, in order to understand concepts, we need to know the term ligand. What is a ligand? Ligand, students, is a species that contains a lone pair. Now, what is the point of having lone pair of electrons? With the lone pair, if we go to AS chemistry, the chemical bonding part, if the lone pair is donated, we can form a dative covalent bond. So this lone pair of electron can form a dative covalent bond with the central metal atom or ion, or I just say with the central transition metal atom or ion. So that is the difference. A, we're stuck to transition metals, not transitional, it's transition metal. Or B, it can be an atom or an ion. That is what ligand is all about. The next part, the types of ligand. This is basic. This is very basic. But why is it important? Because in the papers, especially in this year's exam, I am certain of the fact that you will be getting definitions, some basic concepts. So we need to talk about the type of ligands. The first type is a monodentate ligand. Now, what is a monodentate ligand? Mono means one. So, a ligand that shares only one electron pair. Just one. Obviously, to form a dative covalent bond. Now, monodentate ligands are further divided into neutral and negative ones. So, neutral monodentate ligands when we talk about the neutral ones, there are two examples. If you go to your AS concept of organic, we talked about these neutral ones as well, but they weren't the ligands at that time. What do we have here? We have water and we have ammonia, NH3. Now here, water's oxygen has a lone pair and here nitrogen has a lone pair, and they share this lone pair. They do not have a charge. As you can see, there is no charge. So they are neutral ligands. They can form dative bonds with the central metal atoms or ions, which we would see. Furthermore, the other ones are not neutral. They are negatively charged. Now they are a ligand, but they will have lone pair. It's very easy to remember. Fluoride ion. Chloride ion, they have extra lone pair. Since they've received an electron, they have a lone pair to be shared. Bromide. Not just that, we have cyanide here as well. So cyanide, nitrogen, also has a lone pair. So these ones are negative ones. We either have halide ions or we have cyanide ion. So A, we had the first type which was monodentate ligands, and it is further divided into neutral and negatively charged ones. Neutral means there are just two examples, water and ammonia. But when we talk about negative ones, halide ions and cyanide ion. When we go further and we jump towards polydentate ligands. Now students, polydentate has further types. One is simple, a bidentate ligand. As the name goes, it has two lone pairs. One compound has two lone pairs. Two lone pairs because it's bi for dative bonds. Obviously, it will make two dative bonds. That is something you need to remember. Now, there are examples for bidentate ligands. The first example is ethane 1,2 diamine. So, simply just make a structure out of it. We have ethane, C and C, and diamine. One amine here at one carbon, one is the other on the other carbon. CH2, CH2. And where do we have the lone pair? Nitrogen, nitrogen. I can make a skeletal formula out of it just like this way. Because carbon, we never show the carbons. And remembering the older concepts, normal bond is shown this way, while a dative covalent bond is shown with an arrow, because an arrow is transferred. So in this case, students, this will make a bond with central metal atom or ion this way, arrows, with arrows. So as you can see, it can make two. But when we talk about, for instance, water, we'll have one water making one bond with the metal atom, depending on the coordination number that we will talk about later. And even ammonia can be there as well, forming its own dative covalent bond with the arrow. So all of them will make arrows. This was the first example of a bidentate ligand. Now moving on to the other one. The other example of a bidentate ligand is ethane dioate ion. O8. Remember, O8 ion is when you remove hydrogen from an acid. So ethane means two. Like this is an ethane dioic acid. I'm just going to make an ethane dioic acid first. That is an ethane dioic acid. But students, if I remove the hydrogens here, there will be a negative charge and they will have also their lone pairs. So this is ethane dioic acid. And how can we show it? Just like ethane diamine, it has two oxygens, and then we also have this oxygen-oxygen double bond. And these oxygens with the lone pair, they will further make two dative covalent bonds, students. with whatever metal that we have. And this is the type of a bidentate ligand. Now, moving on to the next type. When we talk about polydentate, we only have a bidentate, or jumping on to straightforward to a hexadentate ligand. There's only one example in your syllabus that you need to know, that is EDTA. This name is ample for you. EDTA, this is ethylene diamine tetraacetate. Ethylene, diamine tetraacetate, EDTA. Now the structure, unfortunately, you need to know about the structure. Ethylene means ethane, eth. So we have CH2 bonded with another CH2, and this is further bonded to an N for amine. But N is there. Then we have tetraacetate or acetic acid. So this N is further bonded to 2, and this N is further bonded to 2. Furthermore, N has its own lone pairs, which we cannot forget. So 2 lone pairs for donation. But when we have acetate, this carbon is further linked to, that's 2, CH2, COO, and this becomes CH2, COO. Now, as you can see here, there are 6 lone pairs to be donated. That's EDTA. And it is technically an ion, EDTA ion, with a -4 charge. 1, 2, 3, 4. But with 6 lone pairs to be donated. The structure is pretty complex. Let me show you how does the structure look like. This is what the structure is like, students. We have one EDTA, as you can see. We had OH. Obviously, the H is removed here. We don't have the H anymore. We just have oxygen there with a lone pair. And you can see it quite well that there are 6, 1, 2, 3, 4, 5, 6. 6 dative bonds that one EDTA can make. And the element, the transition metal, needs to have a coordination number of 6. So that is what ligand is all about. So we have talked about the ligand, but let's talk about what exactly a complex is. So complex can be a molecule or an ion, because that depends on the central metal atom and the ligands, because ligands have also charges, and sometimes they depend on both of them, that we will study. So a molecule or an ion which is formed by a central metal atom or ion surrounded by one or more ligands. Why one or more ligands? Because in the case of EDTA, we don't need any other ligand. We just have one EDTA and that's it. So that is what a complex is about. Now, complex compounds have central metal atoms. For instance, let's say if a metal atom is here, that's my metal. I can have hexaaqua ions. For example, hexa-aqua means 6 waters can be there. So technically, it's going to be a 3D shape, but it doesn't serve the purpose here. This does not serve the purpose here, students, because we are not able to find out that what is here. Because OH2, remember, it's always the oxygen bonded. Now, what is a better way to make it? Students, let's recall how the shape can look like. It's making 6 bonds. You need to recall your concepts from AS, chemical bonding. And the shapes of molecules is going to be a part of this chapter as well. We need to make 6 bonds. So they have the same angle in every direction, octahedral shape, octahedral structure, 90 in every direction. It's difficult for me to make, but let's try. So it needs to have an angle of 90 in all directions. So how will we show that angle, students? How are we going to show that? Dot and cross method. Dot and wedge diagram. Let's say these two are dot, simple bonds. These ones away from the plane. And then we make wedge, showing that this is coming towards us. That tells us that how all of them are not in the same plane. That's one thing. So these are how the ligands are arranged. Moving on to the next part. Coordination number. I mentioned this many times during this lecture because obviously I know it, and I hopefully you know it as well. But even if you don't, now you will remember it. So what is the coordination number? This is the number of dative covalent bonds that a central metal atom or ion can make. So that is what it is. The number of central metal atoms. Now, in the exam, you can be given a formula of a complex. For instance, if we have iron here bonded to 6 aqua, which is 6 water, and that's the total charge. Now, we can easily see two things from this formula. A, what is the coordination number? Six, as it is making 6 different bonds. And what is the charge of iron? That is an important calculation. The charge of its whole complex is +3. We know water has a 0 charge. So iron plus 0 equals to +3, which is the total charge. So the charge of iron here is +3. That is how you can find out. For instance, if we have iron bonded to CO and NO2, no charge. What is the coordination number? Coordination number is again 4. We just count the bonds. That is how you are going to calculate what's happening. Now, here iron is making 4 bonds, there it's making 6 bonds. That depends on the size of the ligands. That we will talk about later. That will further change the shape of the complex. But for now, how can even iron make 6 bonds? Remember, let's make the electronic configuration of iron. Iron has 6 3D electrons and 4s2. Now, when we make iron plus 2, this just loses the 4s electrons. Because as I said, 4s are the ones which are lost first. But in this case, it will become 3d5, which is a half fill orbital subshell, and that's stable. So, how can it make those complexes? Now, in this case, it's a neutral atom. It seems neutral. But let's look at iron here. Because students, remember, these are just not normal bonds. These are dative covalent bonds. And dative covalent bonds are involving 2 electrons, not 1. So let's make the electronic distribution with the block method. 3d6. D will have 5 boxes, 5 orbitals. With 6 electrons. And then we have 4s. Which is completely filled. So that's what it is. Now, can this make 6 bonds, and that to 6 dative covalent bonds? I don't think so. It's not possible, because these ones will only accept 1 electron. They cannot make dative covalent bonds. So how can we make dative covalent bonds out of it? So students, for that purpose, let's talk about iron 2 ion, because we have an iron 2 ion here, or iron 3 for say. They're the same. Why are they the same? If we have iron 3, that is what we definitely have, students. For iron 3, even these electrons are gone. But now that we have jumped up into the 4th shell, 4th energy level, we have vacant 4p and 4d subshells. Since 4 is there, we just remove the electrons. That means the energy level, the 4th energy level is there, but with empty p orbitals and furthermore empty d orbital. Now, these can make dative covalent bonds. Since they are empty, they can easily accept 2 electrons. Now, if I have it this way, that is what we can do, students. Now they can easily accept 6 electrons. All the empty ones, 4d, 4p, 4d. The 6 ones are here. So 4s and 4p and 4d can help us accept lone pairs. They can accept lone pairs and make dative covalent bonds, because that is the purpose. Ligands, dative covalent bond. Coordination numbers, dative covalent bonds. So when we talk about complexes, we are not talking about simple bonds. We are talking about dative covalent bond, students. So that is what it is. Now, as I said, let's talk about iron or any other one making different bonds. In the case of iron, we talked about how, where is the, let's say iron can make 2 types of ligands, complexes I mean. This one is iron and there is a square bracket around it, and that shows plus 3. Now, in this case, it's making 4 ones. But when we have this one, iron will just make 4 dative bonds. It's the same iron. Then why is it different here? Why is it different? Why is the same iron making 4 dative bonds and why is it making 3? The difference is the size of the ligand. Smaller the ligand, more can be attached. And if the ligand is bigger in size, if you see and look at these ones, C and O, that's a big one. N and O, that's again a big one. These are larger ligands. So larger ligands have coordination number 4. And big ones, smaller ones can have coordination number of 6. An important example of your syllabus is cisplatin or transplatin, whatever you call it. PT. Platinum is there, bonded with Cl. Now students, how will you determine which ligand is bigger or which ligand is smaller? It's the MR. Simple. Water has an MR of 18, while this chloride has an MR of 35.5. Now this has -2 means platinum is +2. So this is again making a coordination number 4. So it's always with the size of the ligands that you have to determine the coordination number. Now in the exam, they can even test you by giving you a bigger ligand. For instance, and they'll ask you about the charge on the central metal atom or ion. And we don't know what it is. So as we can see, the coordination number is definitely 6. 5 here, 1 here. Coordination is 6. But what is the charge of cobalt? Now we'll use the formula that way. We don't know about cobalt. So cobalt plus, what was the charge of ammonia? It was a neutral ligand. So 0. 5 into 0 plus bromide -1 equals to +2. So we have cobalt plus 0 minus 1 equals to +2. And hence we easily find out that cobalt is +3. This is something they can ask you in the exam. That's a basic one. For instance, let's change it. It's cobalt with ammonia, but this time we have sulfate here. Why am I doing it? Because these molecules can further be used for some other reactions that we'll discuss today. That's a concept of the P3, but the paper P4 has had questions like that. So in this one, we have replaced it by sulfate, the same +2 charge, but we know cobalt charge, we don't know about it. Ammonia is 0, total charge is +2, but sulfate is -2. So when sulfate is -2, that's a different story now. Because in this case, CO is 0 and +2, cobalt has a +4 state. That is how it's different. They look the same, but here cobalt is +2, here cobalt is +4. It can vary. We can do that about platinum as well. For instance, platinum makes a complex this way. Remember, these are not chlorine molecule. This is not a chlorine molecules. These are two chloride ions written together. So, because chlorine molecule is not a ligand. Now, if we have to determine the charge of platinum with the same formula, it's plus 4 here. But platinum also makes another complex with 4 chlorides, and the total charge is minus 2. And here again, platinum, if we calculate, it's plus 2. And why do we have just 4 coordination number here? Because as I said, chlorine is a bigger ligand. There's a problem with the space. The bigger the ligand, the more are the issues with the 360 space. Smaller the ligand, we can easily fit them. So, bigger ligand, bigger problems. Now, these ligands can further make complex molecules, and they can be a part of various reactions. This came in the past papers once. Let's do, like we made cobalt with the bromide at the end. This one. And this has a plus 2 charge. What if I make a sulfate out there? So I just make a sulfate out there. On the other hand, we talked about another one. This one. So we have cobalt, NH3, 5, sulfate. Sulfate is locked inside this time. And since it's plus 2, we will be needing 2 Br molecules. Now there are 2 bromides outside. Unfortunately, you need to memorize the older concepts, especially now. Before we talk about this, AgNO3, silver nitrate, and barium nitrate or barium chloride, or these ones were important. Silver nitrate test was used for halide ions, and barium was used for sulfate ions. This makes barium sulfate, which was insoluble, and this makes silver chloride, silver iodide, silver bromide, and you need to memorize the colors again, because there are various questions in P4 where they ask you that which one has iodine, which one has chlorine. You will react them with silver nitrate and find out the color of the precipitates. White for chlorine, yellow for iodide, pale or cream for bromide. I changed the order. Anyhow, so if we have these ones, we conduct both silver nitrate and barium nitrate tests on these, for instance. Now, in this case, we do have a bromide here. But bromide is locked inside. It has a dative bond with the metal ion. So it will not be easily freed upon. It's locked with the metal ion. So this bromide does not react. Br does not show result. But when we reacted with sulfate, for barium nitrate I mean, this will show, sulfate will give white precipitate. Because it's outside the complex. It is not a part of the complex. And that tells us about the stability of the complex. The one inside the complex is a strong one. You cannot break that dative bond very easily. On the other hand, here we have sulfate here, inside, locked. So barium nitrate test, no result. But bromide will form cream precipitate. These observations have came in the exams before, and they can come in the exam later. So this is the general introduction of the complexes. In the next lecture, we will talk about the shapes of the complexes and how are they octahedral, why are they tetrahedral, even the cis and trans effect. So see you in the next lecture. Thank you so much.